In this video, I'm going to tell you about debugging. In general terms, this is the process of finding and removing bugs from the code. The debugger is a tool that allows us to do this by analyzing the program during runtime. It's not only great at catching runtime errors, but it provides a suite of functionality that allows us to view the current state of the program at any given point, allowing us to find logic errors as well. With the debugger, we can pause the execution of the code at breakpoints, inspect the current state of the variables, step line by line through the code, and even modify values in memory. The debugger should be your go-to tool for solving runtime errors and analyzing algorithm errors. The difference between these two is simple. Runtime errors cause an exception in the game. If the exception is not handled, this will cause the game to crash. These errors can arise from a number of situations. One of the most common runtime errors is a null pointer exception. This error happens when you try and use an object that has not yet been initialized. Other examples are array out of bounds errors, divide by zero, IO errors like file not found, and so on. Algorithm or logic errors do not cause an exception and do not cause the program to crash. Since these errors do not throw exceptions, it can be more challenging to confirm the source of the error and possibly even hard to see that there's an error at all. Examples of these errors can be objects not responding properly to input, failing to find a path when one exists, and so on. Further, the errors can be linked and compounded. Logic errors can cause runtime errors, and logic errors in one spot can cause or hide logic errors in another spot. The approach we use for solving these is different, but both problems can benefit from the use of the debugger. The Unity editor does not have a debugger built in, but we can use the IDE that ships with Unity, MonoDevelop. Since the two applications are separate, it's a little more work to get the debugger working. Also, while later versions of Unity have improved upon this, having the two applications separate has been known to result in problems getting the debugger to work properly and consistently. Let's look at an example by setting a breakpoint in this example code and attaching the debugger. We're going to set a breakpoint here on the first value inside this start method. You set a breakpoint by clicking in the column on the left side here next to the line numbers. A breakpoint is a flag that tells the debugger that when the execution of the code gets to the breakpoint, it should pause the execution and wait for us to tell it what to do. This is great for situations where you want to see what values are being input into a certain function, or if you want to step through the code after the breakpoint. Breakpoints should only be set in the code where a valid execution will occur. For example, setting up here would be invalid. Now that we've set our breakpoint at the top of the start function, let's attach the debugger. The steps for attaching the debugger are to ensure that the Unity editor is open. It is. Then press the play button in the top left of MonoDevelop. This will bring up the attach to process window, and we see that our Unity editor is in here, and we can attach to that. Now the debugger is attached. We can switch back to the Unity editor and hit play. This will trigger the breakpoint that we set. We see the execution of the code has paused. It's important to note that while the execution is paused, we can't actually use the Unity editor because the execution is paused, it won't accept commands. When the execution is paused, we can hover over variables to see what their values are. We can step over code to continue the execution line by line. We can step into functions and then step out of functions. And we can right-click on values and add a watch. Stepping over, this will invert the value of B value. Now we see that the color has changed to blue because it's now true. And stepping over and then continuing execution. We now see the execution is continuing here. We see the values that were output in our function here. Breakpoints are great for a lot of situations, but what about if we only want to break on a line sometimes? That's where conditional breakpoints come in. For example, this bit of code here has a total value which is added to by I each iteration. We can set a breakpoint here, right-click, and go to breakpoint properties. And we see that we're allowed to set a condition here. Break when condition is true. And then we can type an expression here. So when I is greater than 500, we want to break. Say OK. Now the code will break when I is greater than 500. Again, we'll attach the debugger. It's attached. Go back here, hit play. The code now breaks on the value. We'll see it's equal to 501, which is greater than 500. So now we can continue execution, and it will continue to break on that point. If we mouse over I and add a watch, we can delete these watches. Continue execution will continue until the next breakpoint. And since the next breakpoint is inside this loop, we're going to continue hitting it. In this video, I've shown you the power of the debugger and breakpoints. These tools are incredibly useful when solving problems in your code and algorithms. The debugger can also be used as a learning tool. If you're not sure how an algorithm works or unsure how a certain section of code will be executed, step through it with the debugger. The debugger will show you step by step which line of code will be executed next, and you can analyze the inputs to the control flow statements like if, else, for, while, and see why the execution went the way it did.